Welcome to the Single Input Production Economics for Farm Management. My name is Paul Mitchell, and these are a series of lectures for AAE 320, Farming Systems Management. What we're going to do in this section of the course is look at production economics, learning goals. Welcome to a series of videos called Single Input Production Economics for Farm Management. My name is Paul Mitchell, and these are a series of videos for AAE 320, Farming Systems Management. In this section, our learning goals are to look at single input production functions. The next section, we'll talk about multiple input production functions. And what we're going to focus on is what they are and how to use them in production economics, particularly focusing on their use for farm management. It's really all about the economics of identifying optimal input use or optimal input and output combinations. In the simple sense is how much nitrogen fertilizer do I use for my corn? And then if I use that much, how much corn do I get? And it's essentially application of basic production economics to farm management. Well, the first thing we want to talk about is I've been using this term production. What do I mean? It's using inputs to create goods and services having value to consumers or other producers. It's what farmers do, is what production is all about. It's using land, labor, their time, machinery, animals, seeds, fertilizer, water, and things like that to grow crops, to raise livestock, to produce milk and eggs, things like that. These can be sold to the consumers or to other farmers. A farmer can grow corn and sell it to their neighbor who then uses it to grow livestock. They can also further process it themselves. They can take their milk and make cheese. They can take fruit, make jams or jellies. They can take wheat from the farm and make baked goods to sell at the farmer's market. You can also produce services like a bed and breakfast. People come to your place to live the farm experience. You can run an orchard or pumpkin farm with hay rides and sell the fall country experience, things like that. It's not just creating corn and soybeans or milk. We use this term called production function. And what this is, it gives the maximum amount of outputs that can produce for given inputs. There's 2 points I want to focus on is the word maximum, and then what do I mean here? We got 2 different ways of reporting it. The table or tabular form, a production schedule, and then a mathematical function like you learned about in school. The key is it's the maximum amount. It's not how much you can produce, it's how much the most you can produce. So if you give me 100 acres, how many bushels of corn can I produce? The maximum. Not just, can I grow 5 bushels of corn on 100 acres? I hope so. But what's the maximum you can produce? So here's a simple example. These are made up numbers. This is not a real production function by any means, but it's a tabular form. It's a table. So on the first column there is the feed. It's thousands of pounds of TDN per year, total digestible nutrition. So you got 0 all the way up to 14,000 pounds, or I'm sorry, tons, no, 14,000 pounds of feed for the cow for a year. Then how much milk she would produce on average. You don't feed her anything, 0, she doesn't give you anything, 0 milk. And you go all the way down there to more reasonable levels. 10,000 pounds of feed, she produces 21,000 pounds of milk, and etc. So you take the same data, you can make a little plot as well. And so there's a plot. As you go the feed going on the horizontal axis, the vertical axis is how many pounds of milk they produce. And so you can see it starts out slow, rises quickly, and then starts to bend over and flatten off. That's a tabular form of a production function. The other way to do it is as a mathematical function. It's, the single input, it might be milk as some function of TDN, function F. For example, it's a quadratic equation. Milk is equal to 50 plus 3 times the TDN minus the 0.2 times TDN squared. It's a nice little quadratic equation, goes up and makes a parabola, comes down. It could be a multiple input and single output. Instead of feed, it's going to be milk as a function of how much corn, silage, and soybean meal they have. So milk produced in a year might be 50 plus 3 times the corn silage, maybe in tons, minus 0.2 times corn silage squared, plus 2 times the tons of soybean meal, minus 0.1 times the tons of soybean meal squared. Then there's this interaction term, 0.4 times the tons of corn silage times the tons of soybean meal. These are examples of quadratic functions that can express that relationship and make those plots like we just saw on the previous slide. There's lots of other examples though. We've got a linear and quadratic, that's what I've shown you, but you can also have cubics, a cubic, x to the cube, third power. But there's lots of other functions out there that people use in various settings. Depends on the context. Cobb-Douglas is a common one. Von Liebig, or the linear response plateau. It goes up for a while and flattens off. It can be quadratic response and plateau where it rises at a curve and then flattens off. Exponential, asymptotically approaches some maximum amount, hyperbolic. There's all kinds of other functions out there. We're going to stay with quadratics in this class, but I just want people to know there's a lot of options out there. So why do we use them? They're basically more convenient to use in these tables. You can have sets of tables, but once you start having lots and lots of inputs, it gets really confusing. Let's just make a nice little mathematical function. It's very convenient. You can also estimate them via regression. Take your tables of data and convert it into an equation, just doing simple regression analysis. Increased understanding of the production process as well. You take these regression equations, you find out what the coefficient is on some of these inputs, helps you identify which of the inputs is more productive than the other inputs, and which, how important each factor is, the factor of production. Lastly, let's just use the calculus of optimization. So you can actually find the economically optimal amount of each of these inputs to use using calculus tools. This whole process of identifying these response curves, these production functions, and understanding the various impacts of different inputs, it's an extremely common agricultural research scientist activity. They do experiments and then estimate these curves, these response functions. So let's do some definitions here. Just for the sake of this course, I'll be a little fluid in the use of these, but for now, we'll say the input is X and the output is Q for quantity. So the total product is a term that's used sometimes. It's the output Q. What's the total product for a corn? It's how much corn you produce. You don't say Q, you might say yield or something like that, but sometimes the term is total product. Another term that's used in economics is average product, which I'll abbreviate as AP. It shows up a little bit, and I'll explain when, but it's just the output Q divided by the input X. It's the average amount of output for each unit of the input used. For example, let's say you harvested 200 bushels per acre of corn from a field, and you applied 100 pounds of nitrogen per acre on that field. Well, then the average product is 200 over 100, or 2, which means on average, you got 2 bushels of corn per 1 pound of nitrogen applied. Scientists call this, soil scientists call this the nutrient use efficiency in a simple sense. There's also water use efficiency, and you can think of other ways of doing this, but it's the average across all the pounds of nitrogen you apply to the field, on average, how much corn you get. And in terms of graphics, if you wanted to plot this, you drew your production function, you put the point of a line at the origin, the 0 point, and then the slope of the line between the origin and wherever you are on that curve would trace out the average product. It's not the slope of the function, it's the slope of the line from the origin to where you are in the function. The next one is the marginal product, which we'll abbreviate MP. It's delta Q over delta X, or the derivative will be dQ dx, and we'll drive the deltas to infinitesimally small, and then you get the derivative. We'll get to that later in the slides. But it's the output Q generated by, what is the marginal product? It's the output Q generated by the last unit of input used or applied. So back to our example there, how much corn yield increase when you went from 99 to 100 pounds? In this little store, we had 200 bushels per acre, but let's say when you went from 99 pounds per acre to 100 pounds per acre, your yield went up from 199 to 200 bushels per acre. Well, then the marginal product would be the change in Q. 200 minus 199 would be 1 pound, 1 bushel. And then how much did delta X go up? You went up by 1 pound. So 1 over 1 means you got 1 bushel of corn from that last pound of fertilizer applied. That's what the marginal product is. Not the average over all the nitrogen applied, but how much you got from the last amount when applied. In terms of graphics, it's the slope of the production function, total product curve, the response function. So think about graphically, it's the slope of the function as you move around on it, whereas the average product is the slope of the line from where you are on there. And so they're slightly different. Here's a little graphics that explain this visually. The top part is the total product function, the output function, the response curve, and then the bottom two are the marginal product and the average product. So output is in Q, is in green, the average product is in blue, the marginal product is in red. And what you see as you go, we'll start with the marginal product. The green, as you start here, the slope is flat and it's slow, it's low, and then it rises quickly, but then the slope starts to get gentler, and even starts to decrease. So what's the marginal product? It starts out low, very close to 0, but then it quickly rises. And then at this point where the gray line touches the curve, that's the tangency point. It starts to bend over and starts to come back down again. The slope is steeper for a while here, but then at this point it's really starting to bend down. You can see the peak where it bends from sloping upward to slowing down is back here, but it really comes down quickly, and then up here it goes to a negative amount. So the marginal product is equal to 0 when Q is at the maximum. So here's the maximum, that's where it crosses this line. the slope is 0 up there. If we drew a line, it'd be a horizontal line across here. And then if you go out here, the line would actually be sloped negatively, which is this marginal product here. The average product is this red line, and it's the slope of the line from the origin to that point. So like right here, you might slope a line over, and it traces it out. It's going to be slightly different than the average product graphically, and it'll look like this. You can play with this as much as you want with any kind of reasonable looking green line. It's always going to look like this, the average product to marginal product relationship. There's going to be a spot where the line from the origin is going to come down and touch the function. That's going to be that tangency point. That's where the average product and marginal product will equal each other. Marginal product will be decreasing in that point. So average product is above that, above the marginal product before that. Once you go beyond that, the average product will be above the marginal product. So they switch over, they cross at that point. Below that point, marginal product is greater than average product. Above that point, marginal product is lower, average product is higher. This is really the graphics. Most of the function here is going to be, or the analysis here is going to be focused on the marginal product, but there is some connection between the average product and marginal product. So let's put it in a table form here. So we got the input, X, the output is total product, or Q. The marginal product is calculated here, and then the average product. So how do you calculate the marginal product? It's delta Q over delta X, or Q2 minus Q1 divided by X2 minus X1. So we have a simple example here of the marginal product. That first entry is 6. So where's that 6 come from? It's a total product. 6 is 6 minus 0 divided by 1 minus 0. So 6 minus 0 is 6, divided by 1 minus 0 is 1. So 6 divided by 1 is 6. The average product there is 8 as an example. How to calculate that? It's simply total product 16 divided by 2, 8 is what that gives you. I'm going to go down further down the table there. There's a circled one. A marginal product is 5. That's 60 minus 55 divided by 6 minus 5. So 60 minus 55 is 5, divided by 1 is 5. The average product of 8.9, that's 62 divided by 7, and you get these numbers. So that gives you a sense of where these numbers come from and how you would calculate those in this table form. Here's the same data shown graphically. You're going to get that same relationship. They cross at the same point. Below that point, the marginal product is greater than the average product. To the right of that point, above it, it's the other way around. The average product is above the marginal product. So let's do something called a think break here again. What I'm going to do is I've created this table. You've got nitrogen going down is the X, the input. You've got yield as the output, Q. And then I've calculated the average product for several examples, and then marginal product. And then I left a couple out. I want you to calculate these as a think break. Normally we would work these in class. So fill in those 2 missing numbers for average product and those 2 missing numbers for marginal product. Pause the video, do that, and then we'll come back and go over them. So how do you calculate average product? I give you the formula. How do you calculate marginal product? I give you the formula. So go ahead and do that, and then we'll see you on the next slide. So here's a simple answer. I put the average products in blue. It's just Q divided by X. So 75 divided by 50 is 1.5. Here the other one is 150 divided by 125 and 1.2. The margin products take a little more work. You got to get the delta Q over delta X. So delta Q is 105 minus 75 divided by 75 minus 50, you get 1.2. The next one is 0.6. It's 165 minus 150. That's the yield that's at 150 divided by the minus the yield at 125. And then you divide it by that difference, 150 minus 125, and you get 0.6. So that's how you would calculate, or really it's an approximation of the average product and the marginal product in these tabular forms. All right, we want to talk about something called the law of diminishing marginal product. I'm going to go, usually when you hold everything else fixed, as you use more and more of one input, eventually that marginal product is going to start coming down and decrease. What this means is the returns to increasing that input eventually have to start decreasing. This is just a common sense thing that shows up all the time in biological systems, physical systems, social systems. Eventually the marginal product, the gain from doing more of that activity, adding more of that input, it's got to start decreasing. So take a cow. You got a cow, same size barn, everything else the same. You just give her more and more feed. She can give you more milk, but the amount of extra milk she generates, produces each day is going to start to decrease. That first 1,000 pounds of feed, she really gives you milk. But after she's at 20,000 pounds of feed, she's not going to give you a whole lot more milk when you go from 20 to 21,000. The amount decreases. That's what we mean by the law of diminishing marginal product. If you go back to this figure, what it means is it rises for a while, but eventually that curve starts to bend over and not rise so quickly. Early on, the marginal product increases, but eventually that marginal product's got to start coming down the curve. The total product curve has got to bend over. Another example is corn. If you have the same amount of fertilizer, the same amount of machinery and everything like that, and you just keep adding more corn acres, you're not going to keep getting more corn. The same amount is going to slowly decrease. So if you go from 1,000 acres to 1,100 acres to 1,200 to 1,300 acres, no more other inputs. You don't have only adding acreage. You have just as many seeds, just as much fertilizer, and etc. The extra corn you get from adding 100 acres is going to slowly decline, decreasing marginal product. That's all that means. So we spent a bunch of time here kind of going through explaining these production functions, what they are, and their slope, the marginal product, and this average product, Q over X. Now we can ask is how are we going to use them? That's the next section here. We're going to just use them to figure out how much input to use. How much nitrogen should I use for my corn? How many soybean seeds should I plant per acre? You're going to choose each input to maximize farmer profit. We're going to set it up as an economic problem. We're going to first start with a partial budget analysis, and then we're going to switch over to calculation.